Hey, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey Houston, we don't have a problem. Today the point of this video is to talk about graphing. So velocity and acceleration. So if you recall, we've already been doing this, but we're going to just kind of talk these through. This can be kind of a difficult thing to understand. We have what we call a DT, distance and time graph. So let's say that I have a distance time graph that looks like this. Okay. So a person starts and they start moving, maybe they're in a car, something like that. They start moving and they get faster. Actually, they move off. If this is, let's say this is time 10 and this is distance 10. It's super easy, slope. And so they're traveling 10 meters in 10 seconds. So we can say that the velocity is 10 meters per second. Or probably be 1 meter per second because they're 10 meters in 10 seconds, right? So that is that. And so we could then say, what would this graph look like if I did velocity versus time? Now, what is the velocity? It's 1 meters per second over 10 seconds. So this is 0, and this is 10. And guess what the graph would look like? Boom, a flat line where this is 1. Because ultimately what it is that this graph is the slope of this graph. If the slope of this is 1, and it makes sense, right? They're traveling at 1 meter per second the entire time. So I have to illustrate that for 10 seconds, they're moving at 1 meters per second. Got it? And that leads us to the third graph, which is the acceleration in time graph. We've still got 0 to 10 seconds. What would be the acceleration? Now remember, acceleration is the change in velocity. Well, the velocity is 1 at time equals 0, and it's 1 at time equal to 10. The change in velocity is 0. And actually, let me make a note here. When you draw AT graphs, what we actually typically like to do is to draw them with negative. They tend to often have negative values. So this is the acceleration time graph. It's 0 the entire time. Now that's an easy case where we have what we would call a constant velocity system. Let's look at another example. So let's take the graphs and let's do this a little bit differently. Let's go back to this diagram we've had before. And so we've got a car that every second gets 3 meters per second faster, right? He's going 3 and then 6 and then 9. So let's draw this. But we're going to start backwards with the acceleration. So A versus T. And we'll say, from 0 to 10 seconds. We're going to assume it continues this pattern. And what's happening is it's getting faster. If you think about it right here, right? It's getting faster by 3 meters per second every second. And so what we would do, but it's constantly accelerating. This would be 3, and it's just a straight line. We only got 3 seconds given right here. So this would be 3 meters per second squared. That's this number right here. That's the acceleration time graph. Now let's do this with a velocity time. Now velocity versus time, and this is 0 and this is 10. All we have is 3 data points. All right, so it started at rest, so its velocity is 0, right? The car is stopped right here. And now after 1 second, how fast is it traveling? It's traveling at 3 meters per second. So let's say that this is 1 second, and that's 3 meters per second. After 2 seconds, it's now going 6 meters per second. At 3 seconds, it's going 9 meters per second. And we could extrapolate this out to 10 seconds. After 10 seconds, it would be going, 30 meters per second, I think, right? And so this graph turns into this graph. But what would be the distance time graph? And maybe you see this, and I alluded to this in a previous video. He is getting faster. At first, he's at position 0, right, at 1 second. 0 second, pardon me. At 1 second, he is at 3 meters. All right, boom. At 2 seconds, it's not at 6, it's at 6 plus 3 or 9 meters. And at 3 seconds, it's at 9 and 9, it's 18 meters, right? So what happens is this graph is a parabolic graph. So what you're going to see is that you need to be able to kind of go back and forth between these graphs, knowing that, as I go this way, if you will, this line is the slope of this line. Now, we haven't, maybe some of you are in calculus. How do you find the slope of a curve? And in calculus, they teach you how to do that. I'm not going to get into details, but if you have a nice parabolic thing, you get a straight line. It's something called a derivative. And then when you do this, the slope of a straight line is of a increasing line is a flat line, because this, I'm going backwards. It's the slope of this is just 3, so boom, it's 3. Let's cut now to a video of the world's fastest car.
Anyway, I'm delaying the inevitable because I'm a bit frightened. Let's drive it. I've got my specialist timing gear up here. I'm going to launch it. See how quick it really is. Let's do this. Catapulted, and he got up to speed. I don't know what the speed was, but then he just seemed to stop accelerating. It's like he's got a limiter on it, but he got to that limited speed so quickly. Times I've got here: 0 to 60, 2.27 seconds; 0 to 100, 4.31 seconds; and the standing quarter mile, 9.34 seconds. Really, really quick, like off the line. Oh my God, it was nuts. But it seemed to top out before I'd done the quarter mile. What's going on?
Yeah, so you've got good sensations, so that's absolutely what it was designed to do. So this is the official Goodwood car. We haven't changed it since it left Goodwood, and we geared it to do 150. So what that would have done is you've got to 150 ridiculously quickly, and then it's just sat on the limiter.
Now that was cool. So 0 to 60, or eventually they got to 150 miles per hour, right? That was just crazy fast. That would be super awesome. So what's going on in that graph? Let's think about what happened. He has started at position, let's do the DT first. So we're going to go the other direction now. He started at position 0. And then he accelerated, like really, really accelerated, as fast as you could possibly accelerate. So it's going to be acceleration, you're going to get the parabolic thing. But then at this point, something happens. He reaches 150 miles per hour, right? That's where it was limited at in the video. And so we're going to then have a line that's straight, where the slope of this line is 150. To 1, so to speak, like for a second or whatever. It's going 150 miles per hour or whatever. But then, what does he got to do? He's got to stop the car. He then has to decelerate. Now, he's continuing to move in the positive direction. So what happens is the graph starts to do this. As he pushes the brake, and I'm not drawing it very well, it would be a longer curve, probably be more like this. And eventually, the distance doesn't change. At this point, he's stopped. So he's stopped here. He is decelerating here. He's at constant velocity here. And he's accelerating here. All right, so that's the DT graph of our guy, right? The video we just saw. What would be the VT graph? In this case, what we have to do is we have to look at each segment. If you have a acceleration, it's going to look like, boom, like that. That's for this segment. And then he's going to be moving at 150 miles an hour. So that's going to be, I'm just sloping. The slope of that line is this. And then he's going to decelerate from here to here. And so what's going to happen is he's going to decelerate. So his velocity will be negative. All right. And eventually he's going to stop. Probably it took a lot longer to slow down. And then this segment here where it stopped would be just a flat line like that. And I have these slopes that are the same. It would probably be that this was a steeper slope based upon that particular thing. All right, and then the last one would be the AT graph. So what is the slope of this line? This is, we're going to assume it's what we call constant acceleration. So let's say he accelerates at this amount. Oops. You tend to have these positive and negative. And then you would say at constant velocity, that means that what's the slope of this line? Pardon me, what's the slope of, right, this is the slope of this line. And then this would be, slope would be 0. So then the second segment would be down here. And the third segment would be a negative Probably not as negative as big. It'd be like that. I think that you get the idea. I actually erased the board. But yeah, Houston, I think you get it. We don't have a problem.